Hello, I am a very serious chemistry teacher with a very serious cat who is going to definitely screw with today's thing. Whatever, that's just the way it goes. All right, so today, Lab 3, we're going to go over graphing and we're going to go over emission spectra. Cool? Cool. So when it comes to graphing, you want a big graph. Okay, well, not necessarily. Well, no, you do want a big graph. You want a big graph. You want your graph to take up a significant amount of the page. You don't have to take up the whole page. You're probably going to have to do some math, but you want your graph to be fairly large. Why? Because you need to be able to look at your data. That's what the graph is for. A graph is a very powerful analytical tool, and if you have your graph way up here, you can't see jack. Okay, so what you want is you want your graph to take up a fairly significant chunk of the page. That way, when you have your data on the graph, you can see the relationship between the different points. You can see whether it's a straight line. You can see whether or not your data is noisy. You can see all sorts of stuff. When your graph is up here, you can't see anything. Next, the range of your graph. Okay, so say your data, say if x goes from, let's see, 0.13 to 0.19, then you probably want your range to go from 0.12 to 0.20. Why? Because you don't want to leave a whole lot of blank space. You don't want your data to all be crammed down here because you've wasted all your y space. You don't want your data to be crammed all the way over here because you've wasted most of your x space. Okay. So you want your data, or you want your graph to basically cover just your data. Okay, so yeah, go ahead and just fill your graph as much as possible. Now, I don't know what your data would be, but you basically want, you want to use as much of the graph as possible. Okay. You don't want it all down here. You don't want it all down here. You don't want it all down here in this corner. I mean, you're not going to use the entire graph because that's just not how data works. Okay, but you want your data to, fill the graph. Okay, you want your data to be as included as possible. Okay, you don't want empty space in your graph. Okay, as much as possible. Just make the margins, as big as your data, or at best slightly larger. So when you're designing the ranges, the range and the domain of your graph, go ahead and look at your data first, and just say, okay, this is the smallest text, that's the largest text. Boom, that's the range. Let's see, X is domain. That's the domain of my data. Here's the smallest Y. There's the largest Y. Boom, there's the range of my data. Okay. You want your graph to just contain the data. And then you get to do all sorts of awesome analysis. You should use a straight edge for something like that. I don't have a straight edge handy, so I'm not using a straight edge. Straight edge because you want your line to actually be straight. Okay. Because what you're doing is you're making what's called a line of best fit. Okay, if your data makes a straight line. Okay. Okay, so the line of best fit is the line that best models your data, the line that looks like your data. Okay. Your data will have some actual noise in it, so it won't make a perfect line. So your line of best fit will pass as close as possible to all of the points. There's a really awesome mathematical technique for doing the best line of best fit, but you're not going to be doing that. You're just going to be putting a ruler on there, drawing a line. Okay. And that will be good enough. Good enough. Good enough is good enough. Okay. And then you'll be using that line, not your data, but that line in order to come up with this mathematical model. Okay. That line of best fit will get you your y equals mx plus b sort of mathematical curve. Okay. So B is what's known as the y-intercept. That is fairly easy to find. That is where the line passes through the y-axis. So once again, we draw out a graph. We have a selection of data, and then we draw a line of best fit. Okay. This right here is the y-intercept, or B. Okay. That point, the y value, is of that point where it intersects the y-axis. Okay, that is, obviously, it has to be where x equals 0. If x doesn't equal 0 at that point, then that's not the y-intercept. Okay, so be careful about that. X has to be equal to 0, otherwise it's not the y-axis. It's just the line on the far left side of your graph. Okay. Now, for today's lab, we don't actually need that B point. All we care about for today's lab is this guy right here. M is the slope. We love us the slope in today's lab. All right. So the slope is, the angle of that line. Okay, for a perfectly horizontal line, the slope is equal to 0. For a perfectly vertical line, the slope is equal to infinity. Okay. The slope tells us about how much the y value changes in response to how much the x value changes. Okay. So for a perfectly horizontal line, the change in the x value doesn't cause any change in the y value. Thus, m is equal to 0. For a perfectly vertical line, any change in the x value, there's no change in the x value to get a change in the y value. Thus, the slope there is infinite. Okay. Now, this here is a somewhat more realistic line. It is intended to be a straight line, even though it doesn't actually look like one. And the y value does change in response to the x value. It's neither infinite nor 0. Okay. So the way you calculate the slope is this. Okay. The slope is the change in y over the change in x. Okay, this triangle is actually the Greek letter delta, and it means change. So what that is y2 minus y1 over x2 minus x1. So you're going to pick 2 points on your line. Okay? Any 2 points. It's a perfectly straight line, right? So that means that any 2 points should give the same slope. Okay? And then from those 2 points, you are going to find y1 and x1, okay, the x value and the y value of that point. And then you do the same thing for the second point, y2 and x2. Okay. When you do that, you find the difference between y2 and y1, how much y changes, and the difference between x2 and x1. That will give you how much x changes. And then the change in y divided by the change in x will give you the slope. Now, the reason you want to do that for today's lab is because you are finding the Rydberg constant. You will hopefully have already covered a bit of this in class, but the Rydberg equation is this guy right here. All right. So 1 over the wavelength is equal to this constant times 1 over n squared minus 1 over m squared. This is not the m of the slope. Okay? This is a completely separate thing. So the Rydberg equation describes the lines you see in the emission spectrum of hydrogen. Okay, you run electricity through hydrogen, it will give off different wavelengths of light. Okay, you look at it through a spectrometer, you can see what those wavelengths are. If you were to point your spectrometer at sunlight, sunlight would give you a continuous spectrum. Okay. Okay. Hydrogen doesn't do that. For hydrogen, you get very specific frequencies. Okay. with absolutely nothing in between them. And what they've discovered is that those wavelengths, those frequencies of light, can be described using this equation right here. 1 over the wavelength is equal to this constant, and then n and m are integers. We now know that n and m, these integers, represent the energy levels of the orbits of the electrons. Okay, so you put energy in, and an electron will hop up to a higher energy level. Okay, so here we have the nucleus, and then we have the energy levels around it. So n equals 1, n equals 2, n equals 3. Okay, so when an electron gets energy in, it can hop up to a higher energy level. Okay, so that's energy in makes the electron jump up. And then when the electron falls back down, it will emit energy out as a photon of light. So that is what you're going to be looking at, or that's one set of data you'll be looking at, is you'll be looking at different frequencies of light produced as an electron falls from a higher energy level to a lower energy level. Now, hydrogen being what it is, the lower energy level will be energy level 2. Okay. When an electron falls to the first energy level, it releases so much energy that the photons of light coming out are not visible light. They're ultraviolet, and you won't be able to see those. Photons falling to higher energy levels will tend to be infrared, and thus too low in energy for you to see them. The visible ones will be for energy level 2. Okay. So the way this equation back up here works, m is greater than n, because we're talking about the higher energy level and the lower energy level. So in a way, this tells us about the energy difference between those levels in terms of the wavelength of the light that is released when the electron falls from m down to n. So you will be graphing the wavelength of light as a product of these two energy levels. And then you'll be finding the slope of the line produced, and that will be the Rydberg constant. So the way you do that is by manipulating your data so that you can get a straight line. If you were to try and graph the wavelength versus, let's see, m, then you would get this weird, funky curve, and it would be a little bit more difficult to do. But we can do a little bit of trickery so that this will be in the form of y equals mx. The way we do that, so 1 over lambda equals RH times 1 over n squared minus 1 over m squared. All right, the way we do that is, instead of graphing, say, wavelength versus m, we will instead be graphing 1 over the wavelength versus 1 over n squared minus 1 over m squared. Okay. That is a perfectly viable thing to do. There is absolutely no problem with graphing something other than just a straightforward number. You can do mathematical manipulations of your x and your y values, and that isn't at all a problem. That is a very, very common technique, actually, so that a weird curve will instead be turned into a nice straight line. For example, you might have, you know what? I'm not going to go there. So, the data you collect will be m and lambda, where m is the higher energy level and lambda is the wavelength of light emitted when the photon falls from the higher energy level down to the second energy level. So specifically, the values of m you'll be seeing will be 3, 4, and 5. Okay. Let's see. And because of the way visible light works, the falling from 3 down to 2 will be the lowest energy, and thus it will be on the red end of the spectrum. And 5 down to 2 will be the highest energy because it's the greatest separation, you know, the 5th energy level down to the 2nd energy level, and thus it will be toward the blue end of the spectrum. Hey, puppy dog. Here, let's show you real quick. There's the puppy. He's upside down because of the way this is set up. All right. All right, so, and then your wavelengths of light, I don't know what they actually will be, but let's go ahead and call them like 350, 450, and 650 nanometers. So I don't know what they will actually be. Okay. So this would be your raw data. 345, 350, 450, 650. Okay, I just realized what I did there. First off, I got it backwards. 650 is the red end of the spectrum. Then let's go with 550 in the orangey yellow part, and then we'll go down to 450 down near the blue. The other thing I got wrong is that 350 is in the near ultraviolet. Okay, so, and here comes the cat. All right. So your raw data, if you were to put it into a chart, you would have, say, M as your X value would be 3, 4, and 5. And your lambda would be 650 nanometers, 550 nanometers. Yes, cat, that's right. Make sure that you claim that. And 450 nanometers. Okay. And no, do not grab my pens, because if you take the pens, then the dog will chew them and destroy the carpet. All right, so now what you'll do is you'll do your mathematical manipulation on this data in order to get the points that you'll be plotting on the graph. So 1 over n squared minus 1 over m squared, where n will always be 2. So you're looking at 2 squared. All right, so let's bring up calculator real quick. All right. So 1 divided by 4 minus 1 divided by 9 gets you your first x value, 0.138 bar. All right. Next would be 1/4 minus 1/16, because you'll notice that I'm doing the squaring already. So 2 squared is 4, and then 3 squared is 9, 4 squared is 16, etc. So 1/4 minus 1/16 gets us 0.1875, and then 1/4 minus 1/25 gets us 0.21. I'm going to go ahead and make this 500 instead of 450. I'm trying to come up with a roughly straight line here. I know I'm going to have trouble with that because I'm making these numbers up off the top of my head rather than giving you the real numbers. All right. Now, so those are your three. That is the x. x1, x2, and x3. Now, your y value would be 1 over lambda. So that really straightforwardly is just going to be 1 divided by 650 is 0.001538. Okay. I don't know how many significant figures you'll actually have in your values. Technically, this would be 1 and 2 sig figs. Let's go ahead and just say that, boom, they end decimals. So this would round to 154. All right. Now 1 divided by 500, 0.002, so 0.00200. And then 1 divided by, what is that, 450? And that would be 0.00222. All right, so these are our y values. 1 over lambda and how that changes in response to 1 over n squared minus 1 over m squared. So that is what you would be plotting on your graph. Okay, so let's keep those numbers handy. And our graph would run from just below the 0.138 to just above 0.21. I don't have any graph paper handy, but let's say 0.135, 0.14, 145. I think this might be too small. 15, 155, 16, 165. Yeah, that's going to be too small. So let's call this 0.13, 14, 15, 16, 17, 0.18, 0.19, 0.20, 0.21, 0.22. All right. So that goes from just below the smallest x value to just above the largest x value. And then our y values will run from, a little bit above 0.0015 to just above 0.002. So let's go 15, 16, 17, 18, 19, 20, 21, 22, 23. All right. So these are 0.0015, 16, 17, 18, 19, 20, 21, 22, 23. So even though my graph doesn't take up the whole page, my data will take up the whole graph. Be sure to label your graph. So not just the numbers, this is also 1 over lambda, and thus the units are in inverse nanometers. Okay? And this right here is 1 over n squared minus 1 over m squared, and it has no units, okay, because these are just whole numbers, they're energy levels. All right, so our first data point is the 0.138 exactly, so it's going to be right about there, 0.154, so it's a little bit less than that, so here's our first data point. And then 1875 and 0.002, so boom, and then 0.21, so exactly there, 0.222, so boom. Wow, that is a roughly straight line. Good for me. Okay, so now we have that. There's a little bit of noise in there. There's our line of best fit. Okay. Now I'm going to cheat because I know I can't get any actual data from this graph because it's not a piece of graph paper. It's just something I drew by hand. So you should take your data from the line of best fit, your numbers from the line of best fit, not from the data. I'm going to take it from the data just because I'm not using graph paper. You will be using graph paper. Take your data from the graph paper, from this line, take the numbers further, doing the y equals mx plus b, y equals mx from line, not data. Okay, so I'm cheating because I can't take it from the line. That's not something I can really do. You take it from the line, do as I say, not as I do. Okay, I'm, a dad in the 50s. All right, so the way we get our slope would be m equals delta y over delta x. Okay, y2 minus y1 over x2 minus x1. And remember, these are supposed to come from the line. All right, so y2, 0.00222 minus y1, 0.00154. x2, 0.21. x1, 0.139. Okay. So we plug those numbers into our calculator. Oops, what did I do? I just did something. All right, so 0.00222 minus 0.00154 divided by 0.21 minus 0.13, that. All right. Giving us this number right here. This is 0.00956. Now that doesn't really mean anything right now, but this is based on these numbers I made up. This is the estimate of the Rydberg constant. Okay, that is what you're trying to find with the data. The slope here is supposed to be this, the Rydberg constant. Now the real value of the Rydberg constant, you'll be able to compare your answer to the real answer, which is, let's see, 1.097 times 10 to the 9. The real value is 0.01097. If it's in inverse nanometers. Okay. Wow, I did fairly well, actually. Just for having made up numbers, I'm not too far off. That looks to be maybe 5 to 10%. That's wild. All right. So this is, this slope is going to be your estimate of the Rydberg constant. The real value of the Rydberg constant is that. Okay, so you'll be able to compare yours. Okay, this is where you can do a percent error. Take your value minus the real value, and so on. Okay, so that is what you're doing in the first part of this experiment. You are going to be looking at a spectroscope or a spectrometer in order to find these three wavelengths. Okay, going from reddish to bluish. Okay. You're then going to manipulate the data in this way to get 1 over n squared minus 1 over m squared for your x values and 1 over lambda for your y values. You are going to then plot those three data points on this graph. You're going to have to make the graph, and then you're going to plot them. You're going to get a line of best fit. You are then going to take the numbers from the line of best fit in order to find the slope of that line. Don't be confused by the fact that I'm using the letter M multiple times, okay? Or at least try not to be. The slope of that line is your estimate of the Rydberg constant, which you can then compare to the actual value of the Rydberg constant. All right, so that's the first part of the lab. The second part of the lab, you are going to be doing the other thing that you can do with spectra, okay? Namely, these emission spectra of elements. All right, the energy, the light that comes out of elements, or the light that comes out when you run electricity through the gas, is based on what element is in there, because different elements have different energy levels. 1, 2, 3, 4, 5, 6, 7, 8. Okay, cat did not steal a marker. All right, those energy levels change from element to element because they have different numbers of protons. So the electrons fit around the atom in slightly different ways. Therefore, the colors will change. The arrangement of the lines will change from element to element. Therefore, the emissions spectrum of each element is going to be unique. You can use it as a fingerprint. And in fact, this is one of the ways that they identify, that's one of the ways they identify the chemical makeup of different stars, distant stars and distant planets. Even before we were able to send, big fancy machines there in order to, actually take samples, they were able to tell what chemicals were in their atmospheres by looking at them through spectroscopes and saying, oh, that must be this, 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 and this, and these various proportions. So what you're going to do is you're going to look at the emission spectra of a number of different gases using the spectra simulation. And then you are going to look at an unknown gas. And you will say, okay, this unknown gas is this element because it has those lines. It should match one of them. Okay. So you'll compare the unknown gas to these known gases, and doing that, you'll be able to identify what the unknown gas is, because the emission spectrum of each element is a nice little fingerprint. All right, so part A is the more difficult part in some ways because you're doing that mathematical analysis using graphs. Part B, you're going to have to do a lot of writing because you're going to be looking at the emission spectrum of 1, 2, 3, 4, 5, 6, 7 different gases. So you're going to have to take down data. You're going to have to write down the emission spectrum of 7 different gases. And then you'll write down the spectrum of an 8th unknown gas so that you can compare it to those 7. Now be aware, nitrogen, right here in the middle, that one has a fairly annoying looking spectrum because it is basically one giant smear. So instead of trying to write down distinct lines, write down the ranges. Okay, let's go ahead. Oopsie. Yeah, so here are pictures. So you see nitrogen through cheap spectroscope is going to look like that. I don't know exactly what they are going to show you, but instead of trying to write down the spectrum for each individual line of nitrogen, you might want to go ahead and say, well, there's a line here, there's a spectrum of green going from here to here, and then there's a spectrum that goes from green through red from there to there. That might be an easier way to do that. Because otherwise you would be stuck trying to write down line, 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 line. It would be awful. So I would not recommend trying to do that. Instead, just write down a range. It goes from here to here, and from there to there, and from there to there, that sort of thing. All right, so less data, more manipulation in part A. A lot of data, almost no manipulation in part B. And that is lab 3. Remember, if you have questions about doing the lab, instead of emailing me, drop those in the discussion board. I can't be online 24/7. Well, I can, but I'm not going to. So that way I'll be checking the discussion board regularly. And also feel free to chip in and try and help each other out. Teaching things is a good way to learn things. Teaching classes really helped me buckle down and finally understand very thoroughly all of intro chemistry. And, working together is not a bad thing. Don't give each other the answers, of course, but, help each other out. All right. And with that is it for Lab 3. I'll stay on the line for a little bit to see if you have any immediate questions, and then I will go play with my cat.